Hello everyone, my name is Prerna Chavan and along with me there is one more partner, Krishna Makhar, and today we are here to present the hardware description language subjects one of the topic that is system on chip, where we are going to understand the SOC design and its application. Next slide please. So this is the overview that we are going to cover in the entire presentation, where we are going to see the introduction, SOC architecture, core components of the SOC, CPU, GPU, other specialized components, memory, DSP, interconnect and communication within the SOC, power management in the SOC design and manufacturing, SOC packaging and testing, its application and certain challenges that we face together. Next slide, please. So, in detail, talking about what SOC actually is. SOC is the short form for system on chip, which is an integrated circuit that consolidates multiple components such as CPU, GPU, memory, and other essential electronics into a single chip. SOC enables compact and power efficient designs, crucial for devices like smartphones, tablets, wearables, and Internet of Things. SOC combines multiple functions onto one chip, saving space and allowing smaller and thinner devices. SOCs are designed to be power efficient, making them ideal for battery powered devices. Integrating component reduces latency, providing faster processing and enhanced performance. SOC can be reduced in production cost by consolidating multiple functionalities on a single package.
Yeah, hello. I am Krishna Makhar. Yeah, this slide provides an overview of a system on chip SoC architecture, highlighting its key concepts and a high-level diagram of its components. SoC architecture is designed to integrate diverse functionalities such as computing, storage, connectivity, and specialized tasks onto a single chip, which allows for efficient data processing and communication. This integration typically occurs on a single silicon die or multiple dies within one package, making SoC compact and versatile. The high-level diagram of SoC architecture shown here illustrates the various components that are commonly included. The CPU is responsible for general purpose computing tasks, while the GPU, it is a graphics processing unit, handles graphics and parallel processing, which are essential for high-performance applications like gaming or AI tasks. Memory is included for data storage and rapid access during processing. Interconnect system facilitate data communication among different components on the chip, ensuring seamless integration and data transfer.
So moving forward, we have core components of SOC, which includes first is CPU, that is central processing unit. The CPU is able to handle general computing tasks and manages system resources. It typically builds a ARM architecture, that is ARM Cortex, RISC-V, and x86 for specialized SoCs. CPU in SoCs often include multiple cores, that is dual core, quad core, etc., to handle parallel processing.
The core components in an SoC focusing on the graphics processing unit, that is GPU, and other specialized components. The GPU is primarily responsible for rendering graphics, which is essential for visually demanding application in devices like smartphones and gaming consoles. GPU in SoC also handle tasks related to artificial intelligence and machine learning, utilizing their ability to perform parallel processing for faster communication. Popular examples include Adreno GPUs found in Qualcomm's SoCs and Mali GPUs in MediaTek. Beyond the GPU, SoCs are integrated specialized components to enhance device functionality.
The fourth that we have is memory. Memory types include SRAM, DRAM, where SRAM is for high speed cache close to the CPUs, and DRAM as the main memory for active applications. Flash storage for data storage. SoCs integrate memory controllers for seamless data exchange between processors and storage. Then next we have is DSP, that are digital signal processors. DSPs are optimized for processing real-time signals such as audio and video. Used in applications where quick data processing is critical, such as voice recognition and multimedia playbacks.
Next is interconnect and communication within SOC. The interconnect and communication system in an SOC is crucial for ensuring seamless interaction between all components. At the core of this system is the bus architecture, which functions as the primary channel for communication among the various parts. A bus system links components like the GPU, CPU, memory, and other peripherals, enabling data exchange across the SoC. Common bus standards include advanced microcontroller bus architecture and advanced extensible interface, both of which are widely used in SoC to manage data flow efficiency. In high-performance SoC, traditional bus system may be replaced by a more advanced network on chip.
Next up we have is the power management in SoCs, where, where we are going to cover about the importance of power efficiency. Since SoCs are typically used in mobiles and embedded devices, optimizing power consumption becomes a essential and prolonged term where managing a battery life. Power Management Unit, that stands for PMU. The PMU regulates power supply across SoC components, enabling energy efficient operations. Now, what techniques do we have? The techniques that we have for power management are dynamic voltage and frequency scaling, which is DVFS, which adjusts power and clock speed dynamically. Power gating selectively, power shutdowns, unused components. Thermal management to prevent the overheating. As you can see, these are the techniques that are taken into consideration when we talk about SOCs.
Next slide is of SoC design and
Next up,
manufacturing
please.
process. Yeah. Uh, First is requirement gathering. This stage defines the functionalities, performance goals, and power constraints of the SoC. Architecture design. Here the components, data paths, and interactions are planned to establish the SoC structure. Third is logic design. This step involves defining how each function operates using hardware description language to present the chip behavior. Next is physical design. In this phase, the actual layout of silicon fabrication is created, including placement and the routing of components. And last is verification. Comprehensive testing is conducted to ensure the SoC performance as specified and meets all design criteria. In the manufacturing process, advanced process technologies such as 7nm, 5nm, and emerging 3nm are used to improve the chip's density and efficiency.
Next up, we have is SoC packaging and testing, where packaging types are common types includes ball grid array, that is BGA, and flip chip to protect and connect the chip. Testing processes includes pre-silicon verification, the simulations to validate design logic. Post-silicon testing, which are the testings to fabricate chip for performance, power, and thermal characteristics. Quality assurance ensures reliability and functionality across different conditions. All the diagrams have been shown to make it more easier how packaging and testing actually happens when it is considered to be in a SoC, that is system on chip designs. Next slide, please.
Application of SoC uh, are widely used in various applications due to their high performance and low power capabilities. First is consumer electronics. SoC power smartphones, tablets, and wearables by offering high performance processing while maintaining low power consumption. Next is automotive. In ADAS, that is Advanced Driver Assistance System, SoCs enable real-time processing for critical functions like lane detection and collision avoidance. Third is Internet of Things, that is IoT. SOC are integral to IoT application in smart homes, healthcare monitoring, and industry automation. And fourth one is networking and communications. SOC are found in routers, switches, and network controllers managing high-speed data transfers.
Certain challenges that are faced during SOC design and its integration. First, heat dissipation and power consumption. And SOCs become more powerful, they generate more heat, requiring advanced cooling solutions. Second, security concerns. SOCs in connected devices are vulnerable to attack. Hardware-based security features like encryption and trusted execution environments are critical. Third, complexity in designing and testing. SOCs are increasingly complex with multiple cores, AI processors, and connectivity features, complicating testing and verification process. Next, please.
Yeah, thank you.
So here we end up with the presentation. Thank you so much. I'm recording this to